Hey guys, today Blair and I are going to teach you about Pascal's Triangle. Pascal's Triangle is a really cool mathematical way that you can visualize a lot of different mathematical properties. Before we get into exactly what properties Pascal's Triangle helps us visualize, we're first going to start by learning how to build a Pascal's Triangle. So as you'll see in Pascal's Triangle, we're going to start in the 0th row, so at the very top, and we're going to start with a 1. Now, the way that we work is by building down from this top 1. And how we get every single number in each of the hexagons is by adding whatever's to the upper left and upper right of the hexagon. So we'll start at the top, and we start, of course, with our number 1, and we work down from here. So the next thing that we're going to do is move down to the left, and we're going to see we have a 1 here. How do we get this 1? The way we get it is by adding what's to the upper right, so a 1, with what's to the upper left, so that's nothing. It's going to be a 0, and we're going to say that 1 plus 0 gets us 1. Same on this side. On the right side, we're going to see we have a 1. Up and to the left, we have a 1. And up and to the right, we have nothing. So it's again going to be 1 plus 0 gives us 1. Now, if we actually go down here to this 2, so we're moving down to the second row, we have a 2. How do we get the 2? Up and to the left of the 2 is a 1. And up and to the right of the 2 is a 1. So 1 plus 1 is 2. That's how we get this 2 right here. And one more time, if we go down to this 3 right here, we're going to say up and to the right of the 3 is a 2, and up and to the left of the 3 is a 1. And 2 plus 1 is going to give us 3. So on and so forth, going all the way down the Pascal's Triangle. Okay, so now that we know how to actually create our Pascal's Triangle, we're going to show the first thing that we can derive by looking at this Pascal's Triangle, and that's going to be Fibonacci's sequence. So the way that we derive Fibonacci's sequence from the Pascal's Triangle is by following the diagonal of each of these hexagons, each of these numbers, and we're going to add up all of the numbers that our line travels through while traveling diagonally through these hexagons. So if we start at the top, draw a line going through, we end up with, draw a better line, we end up with 1. Now we're going to go 1 down. We're going to draw a line through here. And now you see we go through, and we actually only end up drawing this diagonal through the 1 because we don't count going on the border right here. So we're going to get 1. Next, we move here. Going to go here, go diagonally, and we're going to say we're going through a 1, and we're going through a 1 gives us 2. One more time, diagonally, we're going through this 1, through the 2, out here, and we get 3, because 2 plus 1 is 3. One more time, we're going from the 1 through the 3, through the 1. We're going to get that's 3 plus 1 is going to be 5. So let's make that better. 3. Here's 5. One more time, we're going from the 1 through the 4 through the 3. And sort of a little offset, but that's going to be 7. Right here, 3 plus 4 plus 1 equals 8. And as we continue going through diagonally, this will next be 13, and so on and so forth, all the way down the line. You'll notice we have derived Fibonacci's sequence. We have 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, 3 plus 5 equals 8, 5 plus 8 equals 13, and that's Fibonacci's sequence. The two numbers in front of one number are going to be the sum of that number. And this will continue all the way down to infinity as we go through Fibonacci's. As we go down the Pascal's Triangle, the Fibonacci sequence will increase. The next and last thing that we can use Pascal's Triangle for is for finding the coefficients in binomial equations. So a binomial equation is something like x plus y squared. And what we do is we're going to FOIL this out, right? And we get x plus y times x plus y. And we're going to go ahead and we're going to get x squared plus 2xy plus y squared. And now if we if we look at our binomial, or if we look at our Pascal's triangle, and we see that this is the power of 2, and we go to the second row, we'll see that we have a 1, 2, 1, which neatly matches the exponents of what we have in our foiled out binomial equation. We have a 1, we have a 2, and we have a 1. So now what we're going to do is we're going to look at what happens if instead of doing a binomial theorem x plus y squared, we do x plus y to the 4th power. Now, when we have binomial equations that go to much higher powers, the way that we expand them is by just doing x to the 4th plus x to the 3rd plus x to the 2nd plus x plus y. And then what happens is we're actually going to put in our y's going back in order, so we add another y, and then the y just goes in decreasing order from the other side. So it's going to look like this. And then y. So now we have x4, x3, x2, x1, and then no x, and we have y4, y3, y2, y1, and then no y. Now, what's super cool, this is the cool part, we know the exponents, but we don't know what the coefficients are that are supposed to go in front of these numbers, and that's where we use Pascal's triangle. So if this is to the 4th, what we're going to do, we're going to go to the 4th row, and we're going to see we have a 1, 4, 6, 4, 1. And believe it or not, these are the coefficients that we plug into the equation. So this is going to be a 1, that's going to be a 4, that's going to be a 6, that's going to be a 4, and that's going to be a 1 right there. And just like that, Pascal's triangle helps you find the coefficients for this exponential equation. And this will go on to infinity. If you do x plus y to the 6, you would use the same number pattern for the exponents, and then the 6th row right here would show you exactly what coefficients you're supposed to put in. Thank you very much for watching. I hope you enjoy this presentation on Pascal's triangle.